Good morning. Today's lecture we will continue on discussing this chapter. So let's finish the complements and the negative numbers. As a result, there were three representations for representing the complex or the numbers, the negative numbers. There's the sign magnitude, and there is the two's complements, one's complement system. So we figure out, or we realize that the two's complement are the commonly used in real life. Then the range for each number can be found depending on the number of bits, depending on the register. So it will be, look at the number of bits. So here, for example, if we have 5 bits register, how can we determine the range? It will be 2 power n minus 1, like plus minus. Let's see. So let's substitute 2 power 5 minus 1, which will be 2 power 4. 2 power 4 is what? And don't forget negative 1. 2 power 4 is 16. I forget to put the negative 1. So it will be 16 minus 1, 15. So plus minus 15. That's how we figure out for to determine the range for each bits. This can be for sign magnitude, 2's complement and 1's complement. But we will realize that for the 2's complements, we can find the negative 16. We can find this, an extra number representation. Why we can find it? Because the 0 in each element was representing by 2 numbers, one sign magnitude and 1's complement. But here, in 2's complement, we have only one representation for the 0. So the extra representation that we have, or since the 0 has only one representation, we can use it for representing the negative 16. Okay? Again, so the range will be 2 power n minus 1, negative 1, and when there is 2's representation, we will have the extra one. So why this be helpful, or why we need to know about the range? Because there's something we call it 2's complement overflow. So what does this mean? If this number is out of range, what will happen? So for example, when we have 8 bits representation, so 2 power 8 minus 1, then here minus 1, this will be plus minus 127, right? Then, in this situation, we will say that my system can handle only 127, between 1 plus minus 27, if I have 8 bits. So how about if I make an addition for the 8 bits more than this range, which is if I make an addition between 1 and 127. 1 plus 127 will be 128. 128 is out of range in this case. So how is the system will behave? There will be misinformation. This thing we will call it like overflow. So overflow means misinformation. So let's do, when we do this addition, we will realize that the answer will be totally different than the reality. Another small example, we have, let's assume we have 4 bits. So 2 power 4 minus 1 minus 1. So 2 power 4, which is 2 power 3, 2 times 2. What's the range will be 2 times 2, 4 times 4, 8. I think the formula there will be, yes, 2 power 4, which will be 2 power 3 minus 8 which will make it plus minus 7, right? So the range between plus minus 7, let's assume we will have 1, 1, 1, 1, which is equivalent. Oh, okay, I think in this example I get confused because there is a signed bit here. There's a signed bit here. Okay, let me do it again. I apologize about this. Okay, so here there is a 0, here there is a 0, here there's a correction in the notes. Then we have here 2 power 5 minus 1 minus 1. Then 2 power 5, which is 2 power 4 minus 1, which is making the range plus minus 15. Okay? Then let's do 15. 15 is equivalent to 0, 1, 1, 1, 1, 0. And here the 1 is equivalent to 0, 0, 0, 0, 1. Okay? After making the addition, we will realize the answer is like this. 1 for zeros. Okay, what's the problem? The problem is we know the first bit is associated with the sign. This means it's negative. When we do the 2's complement for this number, it will be negative 16. So do you think 5 plus 1 will be negative 16? 15 plus 1 will be negative 16. It's 16. So we realize that we are adding positive number and another positive number while the answer will be negative. And this is something wrong. So what's the main reason for this thing to happen, which is something called overflow. So that's how sometimes the computer can understand it if we are adding 2 positive numbers and the answer is negative. So which is out of range, which is something wrong. Then in this case, most likely, there will be an error message should occur. So there should be something we call airflow or overflow detection. So if there is something happening like this, there will be, you will see in the code overflow. Sometimes if you have a physical device, you will see a red light bulb is on because there is something wrong happening with the device. And this happens frequently. And I mean, happens a lot in many applications. So as a result, we need to keep in mind and make sure that the system must work within the range. If it is out of the range, then there will be something wrong. And the something wrong here, one example, when you add 2 positive numbers, the answer is negative, then there is something wrong. When you add 2 negative numbers, but you realize that the answer is positive, then there's something wrong. That's how we figure it out. How about if you make positive and negative number or make subtraction? Will we get overflow? No, no way. Because you're making subtraction, you will be still within the range. So overflow occurred when you add 2 positive numbers, and you will get a negative answer, which is you will get inconvenient results. Then this is how we sometimes detect overflow. So it can be add 2 positive, get negative, or add 2 negative, get positive. While we cannot get overflow if we add negative and positive. Keep this in mind. And again, the reason of overflow, because I told you like each processor has its own capability, its own limits. So 8-bit limits can handle between plus minus 127, then and so on. So each system can handle. How about if we add more than that, more than the capability, then the system cannot handle it. What should happen if you if you are not programming this? Then it must be error message happening. You need to program it to make an error message or make an indication, a light bulb. It's called overflow. So this is when we are building our designs. During the coding, how can I detect this? When I see, again, 2 positive numbers will be negative or 2 negative numbers will be positive. Okay, any questions about overflow? So overflow is for your information. It will not be, required in either tests or quizzes. It's just like for your information. Now, there's something called weighted and unweighted codes. So I mentioned about how to represent the numbers, again using to convert the number from decimal to binary, or to represent the binary numbers. We can use any system that we have, like, for example, we can use 4-bit register, 6-bit register, 7-bit register, and so on. Now, there are some standards. I mean, in the previous lectures, I mentioned like 7-bit register, as I said, or 6 bits, or something like arbitrary, or I choose it depending on the microprocessor. But now, there are some standards called standards that use a certain selected bits to represent something. So we call it codes. So there is a code is called BCD, which is based on 4 bits register, a group of 4 bits. This is BCD, is a special function or a special register or a special like microprocessing device or microprocessing program that only capable with handling 4 bits. So whenever we will talk about BCD, then we mean we only have 4 bits register. So BCD is most likely used to represent the decimal numbers. The range, or like 2 power 4 bits. 2 power 4 is what? 2 times 2, 4, 16. Now, here in BCD, we are worrying about not the signed angle. We are just worrying about the 4 bits without the sign. 16. I want this to represent the decimal, because BCD comes from binary coded decimal. The decimal, how many decimal digits do we have? 10, right? So we have from 0 to 9. So we can represent the 0 by a certain representation, 1 by a certain representation. So we can represent each digit by a group of 4. This is called like BCD. As a result, we will realize that we have 16 positions, 16 locations to use for different characters, but we only need 10. So we have 6 extra. X6 will not be used. What does this mean? Let's look at the table of the BCD here. 0, 0, 4 zeros. 1, 0, 0, 0, 1. 2, 0, 0, 1, 0. We know how to convert this. But keep in mind, in decimal or in BCD, each number must be represented in a group of 4. So 1, 2, 3, 4. 1, 2, 3, then here's the 4th digit 1, and so on. So we will end up in decimal in BCD 1, 0, 0, 1. This means we have some locations that is not used at all, like 1, 0, 1, 0, 1, 0, 1, 1, 1, 1, 0, 0, 1, 1, 0, 1, 1, 1, 1, 1. So those are not used. So BCD, just understand that this is a new code that for representing the numbers, decimal numbers, each number must be converted to 4 bits, groups of 4 bits. Then in BCD here, the regular or the normal BCD, it will be as we know. It looks like the table that we used in hexadecimal, like each number has only 4 bits. Okay, clear? And again, why it's called BCD? Because it's binary coded decimal. Most likely we need to make this code or this binary code or this decimal to convert it to binary or to zeros and ones or to binary, but each number will be represented using a group of 4. So as a result, as I mentioned earlier, like 6 values will not be used, which means will be extra. Now, BCD, there is a natural BCD that I just showed you, which is the most commonly used. But BCD, sometimes it might not be efficient, or sometimes there are some modifications different than the normal BCD that we know. So which is something we call it the weighted BCD. One of the best way of using the BCD, the good part, which is it's easy to convert. Just you can convert any binary to decimal to binary, then it will be fine. But for the weighted code, there are some other codes are weighted, but different than what is used to be. Like what? So this is BCD again. This is the most common used. Then here, look at the BCD, the weights 8, 4, 2, 1. What does this mean? This comes from 2 power 0, 2 power 1, 2 power 2, 2 power 3. These numbers. Then the value of 0, 0 times 1, plus 0 times 2, plus 0 times 4, plus 0 times 8 will be 0. The value of 1, 0 times 1 will be 1. The value of 2, 2 times 1, 1 times 2. Let me change the shape, the size. Okay. The value of 1, the corresponding value is 1. 1 times 1 will be 1, right? The value of 3, 1 times 1 plus 1 times 2 will be 3. How about the value of 5? 1 times 4 plus 1 times 1 will be 5. That's how we use this code. This is BCD code. So the weights here, we have 8, 4, 2, 1. This is weight code because depending on the weights that we have down. Okay, is this clear for the normal BCD? Now, there is another code for the same BCD, but we are changing the weights. And now it's no longer like 2 power 0, 2 power 1, 2 power 2. It's like 2, 4, 2, 1. What does this mean? Each number will be multiplied by the corresponding digits. So when we have 1 times 1, which is corresponding to 1, that's fine. Let's go to number 5. Number 5, you will see 1 times 1 plus 1 times 2 plus 1 times 2. You see? Then the total will be 5. For number number 8, it will be 1. For number 8, 1 times 2 plus 1 times 4 plus 1 times 2, which is 2 plus 4 plus 2. This will be 8, and so on. That's how also we figure it out, which is basically by making the multiplication. You are not required to memorize this table, but you need to know how we get these values. So we need to know if we have this number and we have this weight, you need to know how to find the corresponding value, 3. Okay? So this is another code. This is just like the programmers chooses this. So we have the normal BCD, that we have 2, 4, 2, 24, 21 BCD. And there is also another weights in negative. Now this is different. So we see here the weights are negative. What does this mean? Let's look at number 1. Number 1, negative 1 plus negative 2, negative 3 plus 4 will make it positive 1. Then that's it. Then we have also, let's look at number 6. Number 6 here, which is at 8. Then here 1 at 2, so 8 plus minus 2, which is 6. Okay? So those are called weighted codes, which is based on the weights 8, 4, negative 2, and negative 1. Any questions about this, BCD and weighted codes? There is some codes are called unweighted. And unweighted codes, For example, there is one is commonly used, is called XS3. What does XS3 means? It means same as BCD plus 3. XS3, any number that we used to know in the normal BCD, plus 3, or in other words, plus 0011. So you will see like 0000 plus 0.011, it will be like this. 00001 plus 0.00011, it will make it as 0100. And so on, like 011 plus 00011, it will be 0111. Okay? These are new definitions for us, so again, you are not required to memorize what's the content, but you need to know how we deal with this. Like XS3, the same as BCD plus 3. BCD code 8421, you need to know how to use it. BCD code 2421, you need to know how to use it. Just know how to use it. The same way that I explained to you. So you can know how to fill the table if we need to go back to find the decimal, which is how to make decoding this code. Okay? Any questions? Okay, so now BCD codes, again, it's being stored as binary, 4 bits binary, because BCD based on 4 binary coded decimal, so based on 4 bits. You need to be aware of this. Now there is something called unpacked BCD, and it will be stored within 1 byte. Unpacked BCD will be stored 1 byte, and we know 1 byte equals to 8 bits. So some other representations, to make it more clear, we are using ASCII code. I think many of you are familiar with ASCII code, and ASCII code most likely will be represented in hexadecimal values. Why we are using hexadecimals, not binary? Because we can convert the hexadecimals to binary easy by grouping each 4 bits. So instead of making a very large numbers, we can make it a shortcuts into hexadecimal. So in hexadecimal, hexa values, using the ASCII code, and there's something called the gray code as well. So through the notes, let me explain gray code first, then we will go back to ASCII code. So gray code is binary system that's used two consecutive numbers vary by 1. What does this mean? I can make, for example, the table for gray code, and our target is to make it to minimize the code changes. Minimize the code changes. Minimum code changes, such that there will be only one numeric will be changed at once. What does this mean? In the regular code, we used to say 0000, this for representing 0, 0001 for representing 1. Then we used to say 0010 to representing 2, then 0011 to represent 3, right? That's in the normal one. Is this fine? Now in gray code, he will say when we transition from 1 to 2, what will happen? There will be 2 changes happening in zeros and ones. You see here, and this bit will be flipped to be 1, this bit will be flipped to 0. So 2 changes happens. Gray code suggests that, like if I'm too lazy, I don't want to make 2 changes. I want to only make 1 change at once. So what's the best value to go to the next one, to move from 1 to 2, is to make it like 0011. If I make it like this, then I'm only making 1 change, which is changing only in this bit. Changing only in this bit. So I'm making only 1 change. So this is the idea of a gray code. When I move to the next bits, I will change only one bit at once. So when I move to the following number to number 2, what I will change, I can change this to, what was this? To be 0. You see? So only do one change at once. This is the whole idea of gray code. So this is an example here for 4 bits. We have here 0, one change to be 1. Then from 1 to 2, this change happened. From 2 to 3, this change happened. From 3 to 4, this change happened. 4 to 5, this change happened. 5 to 6, this change happened. 6 to 7, this change happened. 7 to 8, I think I missed it up with, come on. 4 to 5, 5 to 6, 6 to 7, this change happened. 7 to 8, 6 to 7, 7 to 8, this change happened. Then 8 to 9, this change happened. 9 to 10, this change happened. 10 to 11, this happens. Then 11 to 12, 12 to 13, 13 to 14, 14 to 15. So you see, only one change happens at once. This is the whole idea of a gray code. Okay? Again, you are not required to memorize this. So just for your information to understand how the codes are operating. So you have a clue. When you read for example, you see this in the table, you can understand how to read it. Okay? Any questions about gray code? So again, the difference is like binary code and gray code. You will see, for example, the 15 is represented like in binary as 1111, while in gray code as 1000. So there will be different values. So don't rely on the weights as we used to do in the past. Now it will be different scenarios, which is different coding. Now we are in codes. We are no longer in converting binary to decimal, decimal to binary as we used to do it in the previous chapter. Okay? So keep in mind this can be something different. So the alphabet representation, we can represent this using the ASCII code, and we can use it, and there is other code is called EBCDIC code. So ASCII code, which is the most likely common, using 128 symbols, 7 bits code, which is 2 power 7 will be 128. That's how we get it. 2 power 7 will be 128. And for the EPCDIC, 2 power 8, which will be 256 symbols. Then in ASCII code, we can make the alphabets, give it binary values. But sometimes these binary values, we will make it as, write it in hexa table. Why? Because sometimes, as we know, it's 7 bits. So for example, 1, 1, 0, 1, 1, 1, 0, for example, something like that. So I can say this is in binary, but I can convert it to hexa by grouping each 4, then it will be in two digits. So for example, this will be equivalent to, I think E, and this is equivalent to 0. Here is 2 plus 4, 6. So I can represent this as 6E instead of writing two long numbers. That's why when you go to the ASCII code tables, most likely the numbers will be written on hexadecimal but the computers really understand this as a binary, not as a hexadecimal. What's going on? Because as a shortcuts, a representation for me as a shortcuts, I will write it as 6e instead of writing it as 01101110, because we know how to make the conversion easy. So, for example, the letter A will be stored as 0100000001. It's hard to memorize this, or hard to do this. So in order for me as a reference for myself or for the programmer, I will say that A in hexa is 41 in hexadecimal. Then it will be easier for me to say like B will be 42, C 43, E 44, and so on. O, B, C, D, until like Z. Then also for the symbols, like the symbol of AND symbol, 00100110, this will be too long representation, even though the computer is understanding this. That's for the computer. That's reference for me, for the programmer. So the computer will understand it as zeros and ones. But as reference for me, I will say, what's the AND symbol when I write the code? It will be 26. Okay? Is this clear? Then, we mentioned that the ASCII code is actually 7 bits. So what we will do, because we need to store it as a byte, so we will make it, the first bit is 0, or we call it the most significant bits is 0. Then we will put the other elements. So it should start with 0, because it will be like 0, then here, bit 7, bit 6, bits 4, bit 3, bit 2, bit 1. That's how we represent in bits, in binary, the ASCII code. Why we make it the first one 0? Because this is the nature of ASCII code based on 7 bits representation. Okay, clear? Here is the table for ASCII code. For example, the character D, it's in 44. Remember that it should be 8 bits, because so the leading will be 0, then make it 0, then we have 1, 2, 3, 4, 5, 6, 7, then here 8. So don't forget to put zeros to make it 8 bits. Then the equivalent for it, group each 4. When you group each 4, 1, 2, 3, 4, 1, 2, 3, 4, it will be 44. Then 1, 2, 3, 4, 1, 2, 3, 4. That's how we get the decimal value. You group each 4 alone. So you are not required to memorize ASCII code, of course, but when you see the table, you need to know how's the corresponding value of it. How to convert this number or this value to be in decimal, or to this value to be in hexadecimal code, or how to write this in binary code. Again, the computer will understand it as a binary, zeros and ones, on and off. But for me, as a reference, I will use the hexadecimal code because it's easy to remember. As I mentioned earlier, like A is 42, B is 43, C is, I think A is 41, C is 42, D 44, and so on. This is for the uppercase. For the lowercase, it has different values as well. So for the lowercase, for example, A is 61, and so on. So here is the table using ASCII code. The leading bits will be 0. So here it should be start with 0. Then we can figure out Deal writes many things in ASCII code. So let me look at, for example, here is like, it can be like as a keyboard, and this keyboard, how the computer will understand it. So let's write, for example, hi. I need to write the word hi in ASCII code. H is what? Uppercase. Let's look at the H uppercase. H is located into here and here. Then H, it will be, don't forget to put the leading 0 because here it should be 4 bits. So it will be 0, 1, 0, 0. This is for letter H. Then don't forget the other part, which is 1, 0, 0, 0, 1, 0, 0, 0. Then you can convert this to hexa if you need, or you can keep it in binary. So this will be 0, 0, 0, 1, 2, 4, 8. This will be equivalent to 8. 1, 2, 4, 84 in hexa. Now the letter I, look at the letter I. Here is I, it's written as lowercase. Go to the table, look for I as a lowercase. I think it should be here. Here's the lower cases. So I start with here, then go here. So I equivalent to 1. Don't forget the leading 0 in every image. 0, 1, 1, 0. Then here we have 1, 0, 0, 1. So you need to convert this. If you need to convert this to hexa, this will be equivalent to, here is 1, this will be 9, this is equivalent to 2 plus 4 will be 6, 6 hexa. So as a result, the words HI will be stored as 4869 in the computer as hexa. But most likely, since again, we are not, the computer is not understanding this as numbers, it will store it as 0, 1, 0, 0, 1, 0, 0, 0, then the other bits 0, 1, 1, 0, 1, 0, 0, 1. That's how the computer understands high. Okay? So on the homework, you will see like write a certain word into the ASCII code. Keep in mind, it's not only the letters, the symbols, even like you can write your email in ASCII code. You can write even the dots in the ASCII code, the @ symbol, everything. So now you can try. Can you write your name in ASCII code? I want you to write it in hexa and write it in binary. You have the table. Keep in mind that all of these digits starts with 0 in the top. ASCII code is used a lot in the computers, computer programming, and the microprocessors. So that's how the computer will understand or store the words. I have a long name. I cannot write it here. It has a lot of characters, so it will take a lot of time. But here's like the idea. You can write whatever using the ASCII code. For using the ASCII code in hexa, it will be two digits. By using the binary, it will be 8s or bytes, 1 byte. 8 bits or 8 digits or 1 byte. So in ASCII code, again, we see like the symbols, alphabets, and some other keyboard symbols. But how about if we need to apply this for different symbols, like for example, other languages? How can other languages support this? In this case, ASCII code is not an option. We need to use an expanding code, and that expanded code that can handle the other languages or other symbols, we can include ASCII within this, which is basically by increasing the number of bits, the number of bytes, using, for example, Unicode representation. Unicode representation based on 38 bits code. So 2 power 38, 2 power, because we have 2 bytes character. So let me explain again. We have 30 bits codes, but we are actually using 16, and we have other 16s as a backup. So 2 power 16 will be 65,536 different symbols. So it can handle a lot of stuff. Then we have the other 16 bytes are still not used, or we can use it later for future in our references. Therefore, we will realize, since we have this like as a 16 bits, which is 2 bytes, it can handle the alphabets of the English, and it can handle other languages. So we still, using the Unicode, ASCII code still valid inside it. All of the symbols are still valid, but keep in mind that, for example, to represent A, it was 41, now it will be 0041. And when we represent A lowercase, it was 61, now it's 0061. Just make leading zeros for the missing bits that we were not familiar in the past. So using the Unicode, we already included ASCII code there. Then we can, for example, include other languages. For example, like Arabic language. For example, the characters, it will be 0600. And some other representations based on the Unicode. So in Unicode, it can handle some other languages, even like Chinese, Japanese, Korean, any other languages can be handled using the Unicode, while ASCII code in the past was being done only for the English. Now we can handle many other languages using the Unicode. So Unicode most likely used in web browsers, in Java, and many softwares. So it can handle all of these languages, no matter what it is. And ASCII code still valid. This is also the nice part. So there will be nothing new for us. Then when you look at the, for example, computer, let me show you the computer screen. You will see, for example, the notepad. So this software, when you store any word that you write, keep in mind that when you want to save it, depending on the code here. So there are different ways how to represent the numbers. So sometimes some symbols, especially if you are using different languages, if you use the default one and save it and reopen it again, it will be like MS. It will not understand this. It will not understand this because the code is different, or they are not using the code that can be familiar with all of these symbols. So sometimes we will, when we are using any notepads, if you are using different languages, you need to be aware of use, for example, with the number 16, not with the number 8, because the number 8 can handle less number of bits. But here we see, I'm not sure if you can see on the screen, maybe not, but we'll use different symbols that can handle larger amount of bits, so it can handle, especially if we are dealing with other languages, not English. Okay, any questions about the codes? Okay, so this is the end of this section, what's called chapter 1. Now let's go to chapter 2. Okay, before heading to chapter 2, any questions about chapter 1 overall in chapter 1? Okay. Now chapter 2 is something different. We will no longer focusing on the codes and focusing on the transformation between binary to decimal and every stuff. We already agreed that we have some codes like BCD, ASCII code, Unicode. So all of this for representing the numbers. Now, after representing the numbers, what should I do? I need to do some action. I need to say, to make a program. So how to make a program or to do something, use this numbers, use this representation. I need to know the programming tools. The programming elements that can be used to do the programming, which is, we call it the logic gates. Like AND, OR gates, NOT gates, all of these gates that you might be familiar with this. Now, let's talk a little bit about the binary logic, then we will go to the gates. So, binary logic are, or as we know, the computers based on zeros and ones, on and off, like transistors. Transistors on, transistors off, which is basically in the logic, it can be yes or no, true or false. So we can use this to represent something, some elements. So we can say the light is on, light is off, door is on, door is off, garage door is on, garage door is off, and something like that. So whenever we mean logic, there should be either on or off. And this is also the nature of the code, so it's called digital logic circuit. Logic, it can be on and off. So logic function, it depends, there should be some inputs and some outputs. These inputs can be either 1 input, 2 inputs, 3 inputs, it depends. What are the minimum number? The minimum number that we can have for an inverter is only 1 input. This is only for something we call an inverter, which is for reversing the sign or reversing the digits. If it is 0, will be 1. If it's 1, will be 0. This is the only logic gate that can accept 1 inputs. The others, the minimum, we need to have 2. The other basic functions. Otherwise, we cannot modify, we cannot make anything without having inputs. So what are the possible logic functions that we are familiar from maybe different courses or even from school? From back school, then we have like NOT operator and OR. Then we have some other devices that can be derived from this, which is called NAND gates, exclusive OR gates, etc. We will discuss this in this chapter. So these gates are, basically we have 3 main gates, which is NOT, AND, OR. Then the remaining gates can be derived from these 3 essential gates. So let's first discuss about these 3 essential gates, then we can derive the other logic gates based on these 3. So these 3 are the most essential ones. NOT operator or NOT function. NOT function, it has only single inputs and it just inverts the value. We have only 0 or 1. This is the only values that we can have. If it is 0, will be 1. If it's 1, will be 0. We are familiar with this. So sometimes we denote it by X bar, or sometimes we use it like X and put this symbol. So either representation should be fine. So whenever you see bar or see this symbol, prime symbol, then prime or overbar, these 2 are fine. Then the logic or the symbol of it is like triangle. And you will see this bubble. Keep in mind, this bubble is a must to be have. This bubble is a must. Okay? We are familiar with this. Not 0 will be 1, 1 will be 0. So this bubble or circle indicates that there will be inversion. If there is no bubble, this means there is no inversion. How about AND? AND looks like you are doing a multiplication, like X times Y. Like multiplication, or like AND. So if we have x times, or if we have z, which will be x times y, 0 times 0, 0. 0 times 1, 0. 1 times 0, 0. 1 times 1, 1. Okay? So, and we need to have, like, the symbol will looks like this, and it looks like multiplication. Then, basically, if any of these digits are zeros, then the AND will be 0, otherwise it will be 1. How about if we have more than one inputs in AND? How about if we have 3? Like x, y, z, and here is the function f. Basically, we will say that f equal x, y, z, the multiplication. How can we manipulate this into something we call a truth table? You need to keep in mind that when you build the truth table, you need to make sure that 2 power number of inputs. So here, in the past, we have 2 power 2, then 4. So we have 4 possibilities. That's why we have 1, 2, 3, 4 possibilities. Now, how about if we have 3, then it will be 2 power 3, then we will have 8 possibilities. How can we manipulate this into a truth table? Make x, y, z, and here is f. So 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Now let's count them. Are those 8s? 1, 2, 3, 4, 5, 6, 7, 8. Now, how to figure out the function, or the output function? It will be x times y times z. So 0 times 0 times 0, then it will be 0. 0 times 0 times 1. Whenever you see the number 0, it should be 0 because they are multiplication. 0, 0, 0, 0. Then the only output is 1, which is the last one. Okay? Does this make sense? Now, how about OR function? OR function is based on looks like addition. So here, when we have 2 inputs, 0 plus 0, 0, 0 plus 1, 1, 1 plus 1, 1, 1 plus 1, 10. That's why I said looks like. So we will not write in it will write 1 because only 1 bits. Okay? So in logic, here, it will be like x plus y. But keep in mind that it will be, if any of these digits will be 1, then the output will be 1. How we determine the truth table size? 2 power number of inputs. 2 power 2 will be 4 possibilities. How about if we have, and the symbol actually also looks like this. How about if we have 4 or 3 inputs, like x, y, z, and here is f. So the truth table will be 2 power 3, will be 8 possibilities. Then here is x, here is y, here is z, here is f, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. So those are 8 possibilities. Then the outputs will be, here since this all zeros, this will be 0, then the remaining will be 1s because we have 1. Whenever we have 1, this will make the output 1. Just when you see the number 1 here. But in the past, when you see the number 0, we'll make it 0 when it was in AND. But in OR, whenever you see the number 1, then they all will be 1s. So it looks like straightforward because we already know how to deal with all of these stuff. Any questions about AND and OR? Now there is something called timing diagram. Timing diagram, which is like something that's happening every certain period of time if there is an action. So let's assume that I have a switches and at this certain time I change the switch status. So there is function with time happening with this. So in the timing diagram, here is the input x, here is the input y. So what you need to do, we call it each clock cycle or each cycle, I need to make sure to explore what's going on, what's happening. So we can say this is a clock cycle, or this is a cycle happening here. There is a cycle happening here. There is a cycle happening here. And there is another one here as well. So let's assume X and Y already being given. Now we need to calculate X, and we need to calculate AND, OR, and NOTs. So whenever we have here 0 and 0, here we have 0 and 0, their AND, of course, will be 0, their OR will be 0, their NOT will be 1. Clear? Now, whenever we have 1 at X, Y, 0. So their multiplication will be 0, their addition is 1, NOT of X, which is NOT of 1, will be 0. Okay? Just straightforward. How about here we have 1, X, and Y is 1. Now their AND is 1, their OR is 1, the NOT of X is 0. Now how about if we flip X to be 0 and Y is remaining 1, then their AND is 0 and their multiplication is 0, their addition is 1, then the NOT of X is 1. Then the last one, how about if we have here both zeros, 0 and 0, their AND is 0, their OR is 0, their NOT is 1. The NOT of X1, X bar is 1, X bar or X prime. Okay? Any questions? Here is this slide summarize everything related to the truth table for each one. Now, there is something that I didn't discuss called buffer. Here, buffer is the same as the inverter, but no bubble or no circle on it. If it is no circle, then don't do the inversion. It will be remain as is. So you'll see 0 will remain 0, 1 will remain 1. This is the difference between inverter and buffer, which is the existence of the circle. When there's a circle, this means do the inversion, or this is inverter. If there is no circle, it's no longer called inverter, it's called buffer. This means the value will remain as is, no change at all. It seems that like we have this is useless, like it's the same way, nothing happening. Okay? So this are 4 that I will stop here today because we will start the quiz. Then next lecture, I will start with the other digital logic gates so we can figure out how to use them. Thank you.